Hello, so this is homework 1, part C. Before we get into the whole collapse section with all these four tasks for that, we're going to be deriving our, expressions to solve for bubble and dew pressure / temperatures for an ideal binary mixture. So let's start with Raoult's law, and that would be the liquid composition times Pi sat, pressure at saturation, times our vapor composition times the pressure. And to find our bubble pressure, we're going to use Raoult's law. Bubble pressure. So let's go ahead and write our equation down and find the sum. Also, one thing to note, we have a little gamma value, but it's going to be equal to 1 in this case due to the fact that this is an ideal binary mixture. So we can just go ahead and neglect this. However, for the case of bubble pressure, if we do the sums, our summation of our vapor composition equals 1. So this kind of makes it a little bit easier to solve. Our pressure will equal the sum of our liquid composition times our saturation pressure. As for dew pressure, I'm going to go ahead and write down the equation again. However, in this case, we have two unknowns, our xi and our p. No, that's really bad. So essentially, since we're already trying to find p, let's go ahead and try to find for the xi value. So we have yi over pi set times pressure, and go ahead and take the sum of both. However, in this case, for dew pressure, our liquid composition will equal 1 after we've taken the sum, and our P will equal 1 over our yi over pi sat. And there are our bubble pressure and our dew pressure equations. However, for bubble temp and dew temp, it's going to be a little bit different, and explain why. So let's go ahead and write down our sum of xi pi sat equals the sum of yi p. However, if you take the sum of both sides, it just equals out to 1. Since we are looking for temperature, not pressure, there is a little bit of a, component here. So realistically, we can't use Raoult's law to find it. However, we can find roots using collab, and this Raoult's law equation wasn't designed to find temperature per se. So we have Clausius-Clapeyron equation and or the Antoine that could help us solve for this, and we're just going to use collab to go ahead and solve for that. Okay, so what we're going to be doing now is the coding section, and essentially we're just going to go through what we need to do. So we're going to be calculating bubble and dew temperature and pressures along the composition of the nascent vapor and liquid phase, and we're going to test the function assuming that the benzene and the toluene form an ideal liquid and vapor phase. And we're going to be generating the binary VLE diagram for the benzene and toluene at a constant temperature of 360 degrees Kelvin, And we're going to do the same for a constant pressure of 1 bar, and then we're going to generate the XY diagram at a constant pressure of 1 bar. So let's just go ahead and get started. So P equals props, and this is going to be benzene, toluene, and then shift enter. There we go. And then we're going to define our equations that we found. So for bubble pressure, we're going to use the variables x and t representing the liquid phase composition, and then our temperature. So let's start with defining our yp, which is basically saying this side is equal to this. So what is that? It is x times p dot pvap. Yep, at a specific temperature. And then we're going to define our pressure, which is just the sum np dot sum of yp. And then we're going to return with our pressure and yp divided by p. Shift enter, there we go. And we're going to define our dew pressure. So like before, what we used was the liquid phase composition. Here we're going to use the vapor, which is y t. So this time we're going to define what our pvap is, which is p dot pvap at a specific temperature. And then we're going to define this, which p equals 1 divided by np dot sum of y times p divided by pvap. Might have to double check if that's correct. And then we're going to return with p and y times p divided by p. And this should be that. Alright. Yep. So just to note, I did change this y from y times p to y. That's how this equation is, because of our p is going to be on this side, so it wouldn't make any sense to multiply it by p. But that was just a little mistake there. But what we're going to do now is we're going to start by defining our bubble temperature, and we're still going to use the liquid composition, but instead we're going to use pressure this time, since we're trying to find temperature. And since we don't have Raoult's law to use, we need to find our roots. So we're going to come up with a function called fruit. So let's start with looking at T naught, which I'm going to name as np dot sum x times p dot tb times the pressure. And it's just saying x is multiplied by the temperature at a given pressure. So this is how we're going to be able to do that. And then we want to define our fruit function in terms of t, and we're going to return bubble pressure as yep, yeah, I got it for us. So it's going to be the xt times 0 minus p. And then we're going to define what our temperature is. So this will be our sp.optimize.root underscore scalar, and we're going to put our function scale per se, and our method will be secant, and we're going to have dot root at the end, just to make sure everything's work. Yep, that's working. And then we're going to return with t and x times p dot pvap divided by p. Yep. And then for defining our dew temperature, we're just going to copy over because all we really need to do is change all the x's to y. And here we're going to have y, except this is multiplied by p, and our p dot pvap is going to be here. There we go. Just run all real quick. Everything looks good. Now what we're going to do is try to find our binary VLE diagram for the benzene toluene at a constant pressure or temperature of 360 Kelvin, and then we're also going to repeat that for in terms of constant pressure of 1 bar. So let's start with the temperature. So we're going to define what our temperature is, which is 360 Kelvin, and we'll use x1s, which are our list of our liquid composition values. Do np dot line space, and we'll do 0, 1, and 21 values or data points. And then we're gonna start with listing our list of pressures, and y1s is our list of vapor composition values. And then for x1 in x1s, our p and y value is going to turn into an array in the in terms of bubble pressure. So if we take our bubble p and make np dot array, and I guess I already did that, and then we're also going to be doing pressures dot append for pressure, and then y1s for our initial or first value. And yep, this is the code essentially to calculate that graph, but we need to display the plot so that we can get paid. So fig equals make underscore subplots. We're going to do fig dot add underscore scatter, and our x will equal x1s, and our y will equal our pressures. And let's give the name bubble p. And then we'll do the same for our y, or for dew point, or the dew pressure. Except x is going to equal y1s, and y will equal pressure. And then our name for this will be dew. And then we'll also do our layout, which set width as 600, height as 400, and there we go. Here is our VLE diagram in terms of a constant temperature of 360 degrees. And one thing to note, the bubble point or the bubble pressure seems to be very linear as compared to our dew pressure. So that's pretty interesting. Okay, so now that we have our constant temperature VLE, we should go ahead and find our constant pressure. And actually, it's going to be quite similar. So let's just go ahead and copy and paste. However, there's going to be a few things that we want to change. So since we are taking it in terms of bar, but the units need to be in pascals, so we're going to make it 1 times 10 to the 5th, and then change up some of our variables. So we're going to have P, and this is going to be in terms of temperature. So anything we see there is P, because we're going to be looking at and for this we'll change to T. This is also T, and then we'll switch our, that should be, we missed one more right there. That should, nope. Let's let AI do its thing. Okay, I did find a little mistake. So initially I thought this was supposed to be in brackets, but actually it's supposed to be equal to each other. I think that should work. Yes, there we go. And also one more thing. This was bubble. I changed it to dew. And there we go. So we have our plot, and noticeably it is inverse of the constant temperature one, which kind of makes a lot more sense conceptually. As your temperature increases, your vapor composition is going to increase, as liquid will evaporate. And here, as your pressure decreases, your vapor composition will increase. And a little bit about what this graph is trying to say is, given at our constant pressure and our given temperature, if you just scale it, suppose it's 370 or 360 in this case, if we just take it by this line, we have 0.65 as our liquid composition, and then your vapor composition will be 0.82. Yeah, is that, yeah, 0.82. So that's sort of what it's trying to say. You can do the same for here, except it will be reverse of that. Okay, so for our last one, we're just going to generate our XY diagram for benzene and toluene at a constant pressure of 1 bar. So let's just go ahead and write this out. So fig equals make underscore subplots, and then add underscore scatter, kind of. So we have Y1S rather than PS, and give a name, we'll just put mode, and then add scatter, and this is adding a sort of, I guess, a 45-degree line that acts as a, I guess, a reference, which x equals at point 0 and 1, same with y, which is at 0 and 1, and mode will be lines, and then line underscore color will equal the RGB, A being the like transparency factor, I would say, and so 0.1. That should, yep, there we go, and then we can go ahead and, alright, and here is our chart, and if you can see, it is very symmetrical, and the reason as to why is because our benzene and toluene sort of composition has a very constant relative volatility as it's going up. So, yep, and then as mentioned before, it's kind of just proves that for every, I guess, point that you have for a composition, on the other side you will have another composition in terms of vapor and liquid.